Everyone, I'm Pam Cole with the Pacific Northwest National Laboratory, and I'd like to welcome you to today's Energy Code webinar on daylighting controls for commercial buildings. We hold a webinar the second Thursday of every month at the same time, so you can keep a watch out on the Building Energy Codes training page as topics get added. And if you have any topic suggestions you'd like us to consider, please email them into us using the same email in your webinar reminder messages that you receive for registering for this webinar today. So our speaker today is Raul Ashley, and he's also with P&L. And we really appreciate him taking the time to share information on daylighting control requirements. And Raul, it's all yours. Take it away.
All right. Thank you. Thank you, Pam. So welcome everyone, and thank you for coming to this daylighting controls webinar. I'm just going to provide a brief background about myself. I'm a mechanical engineer, and I studied daylighting while doing my graduate thesis at NC State University. After graduating, I worked at an architecture engineering firm that specialized in designing schools, and especially daylighted schools. So I got to experience some of the basics of daylighting design up close. After coming to P&L, I worked on codes and standards for the past several years, and I have participated in the development of daylighting requirements within 90.1 and the ICC. So that's the background that I'm coming from, and my intention with this presentation is to provide an inside view of daylighting and controls. So we start by going over the basics of side lighting, top lighting, illuminances, and so on, and then go look at some of the factors that affect daylighting. From there, we'll go to daylighting controls, see how controls work, how energy savings are realized, and what are some of the factors that affect energy savings. And finally, we'll conclude with the latest requirements in codes and standards that fall under daylighting controls. So that's a brief overview of the presentation today. All right. So let's start with the basics. Why do daylighting in buildings at all? So as it turns out, and as you've probably experienced yourself, humans like natural light. Even when we are indoors, we want to know what's going on outdoors. And in fact, a lack of natural light can lead to depression and is called the seasonal affective disorder, or SAD, or SAD, probably an apt acronym. So we definitely need to be indoors to get work done, and at the same time we like natural light, and windows provide that connection for us. Windows provide a way for natural light to enter the space. You can also bring in light from the top using skylights, but what windows do is they also provide you a sense of connection to the outdoors, which skylights don't. The sole purpose of skylights is to provide natural light. And to generate energy savings by being able to turn off the artificial light, whereas windows also serve as a connection to the outdoors. You can have separate clear story windows at the top of regular windows, which are specifically designed for daylighting. And here we see what happens when when natural light is coming in through a window. The light level near the window is quite high, and as you move inside deeper into the space, the light level keeps falling rapidly, almost exponentially. If you increase the head height of the window, so if you were to make this window higher, or if you were to put more windows at the top here, you can probably get more daylight deeper into the space. The decreasing availability of light as you move deeper into the space is a typical, or is a peculiar problem with side lighting. This is not true in top lighting, where you get a more uniform distribution of light level below the skylight. You can get an even wider distribution or a more uniform distribution if you were to increase the ceiling height. So by increasing the ceiling height, you can get both more wider distribution and probably more uniform distribution across the space as well. So when we talk about daylighting, we often talk about foot candles and lux. And it's important to understand what these units are and what they mean precisely. So all these terms are foot candles and lux. They're related to illuminance. And if you were to shine a flashlight on a portion of the ground, the amount of light falling on the surface would be measured as the illuminance, whereas the brightness of the surface as perceived by you would be measured as the luminance. So the illuminance measures the amount of light falling on a surface, whereas the luminance measures the amount of light emitted by a source or the surface. And these two quantities have different units. Illuminance is the one that we are all more familiar with, probably, especially when it comes to daylighting. It is measured in terms of lumens per meter square or lux, and lumens per square feet, which is called foot candle. A crude conversion between lux and foot candle is about 10. So one foot candle is approximately equal to 10 lux. Here is a logarithmic scale showing illuminances that are commonly found. We start at the very bottom here with moonlight. Actually, you can get there is a quantity that is even lower, which is still perceived by the human eye, which is starlight. Starlight is even farther below here, and you can still see things under starlight, which is basically just the light from stars. So we start at the bottom here with moonlight, which is 0.5 lux, and we can go all the way up to 100,000 lux, which is sunshine, bright sunshine outdoors. And in the intermediate range, we have all these different levels. So at 5 to 10 lux is about what you get from street lights. 200 lux to 2000 lux is the range of illuminances that you'll find recommended for office buildings, for schools, for the industries, and so on. 10,000 lux is about what you would see under an overcast sky. But you can see that this is an incredibly wide or large range, and the human eye is able to adopt all the way across this range. And in fact, even we are able to read things that are under light that is even brighter than sunshine. This is almost a 2 trillion fold range that under which we can still see things. A lot of research has been done in understanding how much light is required in different spaces and to perform different tasks. So, for example, if you were to go out to dinner, you probably don't need as much light. In fact, you prefer the lights to be dim, or some candlelight dinners. I mean, there you go. But at the same time, if you are repairing a watch, which is a very fine and small task, then you probably need a lot of light. And so these recommended illuminance levels, these are from the IES handbook, the 1998 edition. Since then, there have been new editions, and they keep changing these recommendations. But the range is approximately, these are the approximate ranges. So you can, as you go down this list, you see that there are three main things that determine how much light is needed: the type of the task, the contrast level, and how long you need to perform the task. So simple tasks like, maybe just sitting down in a lobby, they don't require much light. But if you're reading or if you're typing, then you start requiring more light. And as you go on increasing the size of or decreasing the size of the task, for example, if you are working on jewelry or if you are trying to read fine print, you probably need more light. If the contrast level was low, you need more light. And of course, if you are, at the bottom here, you have an activity which is performing very special visual tasks of extremely low contrast and small size. So that has a very high recommendation for the luminance level. All right. So when a space is designed for daylighting, there are several factors involved. And generally, we start by asking how much light is needed in that space. So that refers to that previous chart. Daylighting cannot generally supply very high light levels needed for certain tasks, such as if you're working with jewelry and so on. But daylighting can generally supply ambient levels required for moderate office work, just typing, reading, writing, and so on. I don't have a slide in here, but glare is another important consideration when it comes to light and daylighting. Actually, I should go back to the previous slide. Glare is another important consideration when it comes to lighting or daylighting. Glare is when you have an extremely high contrast between the brightest and the darkest part in your field of view. So this is akin to driving on the road at night when you have other cars, someone is having their full or high beam on and it shines the bright light in your eyes, whereas the rest of your field of view is not as bright. And so that creates the high contrast situation, which is called glare, essentially. But there is also glare when direct light falls on your computer monitor, and of course that's not comfortable at all. It is also not comfortable to read when there are wheeling reflections. So if you're reading off of a shiny piece of paper or something and there are reflections, if you're reading in direct sunlight and there are reflections, that can be uncomfortable as well. So there are some recommendations for glare and contrast. You generally want about a 1:10 ratio between the brightest and the darkest object in your field of view. And in general, of course, in daylighting, if you're considering offices and schools, then direct light on the work area, on the work surface is not, of course, it's not recommended. So again, when it comes to, now we are so those were the illuminance levels that are recommended for different tasks. Now we are looking at the factors that affect the actual daylighting design. And one of the big ones is where you're located. Across the US, of course, there is a big change in the latitude as you go from the southernmost parts to the northernmost parts of the country. But also there is a change in the amount of sunshine that you get in different parts of the country. For example, if you're in Seattle, you get mostly diffuse light, and you probably need windows with very high visible transmittance, or at least high visible transmittance. So that means that you need clear windows with clear panes of glass. Compared to that, if you're in Phoenix, where there is a lot of sunshine and probably the light level available outside is very high, you don't need very clear windows. In fact, probably solar heat gain control is more important, and so you want windows with a low SHGC to control your solar heat gain. Most of Europe is also cloudy, and so you can consider the weather, in Germany especially, probably similar to that in Seattle. Okay, as I mentioned earlier, latitude makes a big difference as well. These are some images here showing different views in offices under different conditions outside, and how that can affect the amount of light you're getting inside. So the next key variable is orientation. My advisor, graduate advisor in NC State, he used to teach a course on daylighting, and he had hammered it into all of us that orientation is the most important factor to consider when doing daylighting design. In fact, if you get the orientation of the building wrong, you're pretty much doomed. Everything else is just a band-aid. So these are some rules of thumbs here I have at the top. In general, if your glazing faces north, you mostly get diffuse light, at least in the northern hemisphere. In the southern hemisphere, the south and north would be reversed. But in the northern hemisphere, north mostly means diffuse light. There may be some periods in peak summer when the sun will swing to the east and west of north. So you may get some direct light in the late evenings and early mornings from north, but for most of the time it's diffuse light. On the south, it's variable. In the summer, the sun is high in the sky, and so if you put some overhangs, you'll get probably mostly diffuse light. But then in the winter, when the sun is low in the sky, you probably get direct light, and you probably want some of that heat as well to heat indoors. East and west are generally bad orientations to do daylighting. That's because the sun in the evenings is so low in the sky and so head-on that almost no solution to control that glare works. It is akin to driving on the road with your sunglasses. I mean, sunglasses are probably the only solution that will work when the sun is facing you straight ahead. So I took this picture recently when I was in Salt Lake City for a conference. This is a federal courthouse. I think it has been newly designed. And it looks like it is a full glass building. It has glass on all facades. And it looks like they've attempted to do some kind of shading. I couldn't get very close to the building. This is a picture from across the street, as you can see. But I was walking back to my hotel in the evening, so I took this picture first, and I thought, wow, this is quite impressive. They have applied shading to control the direct light from hitting the glass facade. But then I turned around the corner, and of course, when you look at it head on, it was quite glary. So I cannot imagine that this solution is working for all periods during the day. Maybe it does work for the majority of the day. It's hard to tell without actually being inside the building. But you can see that it's very, very hard to control the direct sun on the east and west orientation. Okay. So the next important variable is interior surface finishes. It can have a large influence on the perceived brightness of the room. This is a picture that I took of a school which I was studying back when I was doing my graduate thesis. So these two classrooms are absolutely identical in every way. The only difference being the carpet in one room on the left-hand side and the lack of a carpet in the other room. And you can see that there is quite a big difference in the perceived brightness. I mean, both rooms still have enough light to be able to turn the lights off, but the right one just looks a lot more bright and airy compared to the left. So yeah, interior surfaces have a big influence, especially the floor and the ceiling tend to have a disproportionate impact on the perceived light level in the room. So that's something to be mindful of if you're doing daylighting design. And finally, the last most important factor are humans, those pesky humans. This is again from the same school, and you can see that it's a beautifully daylit classroom. It has this light light shelf device which diffuses light into the room. But in one of the classrooms, they wanted to darken the space, and the blinds at the top of the clear story were not working. So basically, they found their own solution to darken the room. And essentially, once this solution went in, it stays there forever, and that's the end of daylighting savings. So humans are a very important factor when doing daylighting designs. People will figure out a way to make themselves comfortable. And of course, all of us have probably at some point or another, blocked off a diffuser from blowing cold air on our necks. So we've all been there. All right, so that was an overview of some of the basics of daylighting. and some factors that affect daylighting design. Now we're going to look at how daylighting controls work. The main principle of daylighting controls is pretty straightforward, really. When the sun shines, we get natural light within the space, and we've seen how the natural light level falls as you move inside the space. We are looking at side lighting right now. The natural light level falls inside the space, and in response to that, we can turn off the artificial lights. So you can see that these are 3 lamp fixtures. You can turn 2 lamps off in this fixture, which is closer to the window, because you have a higher light level here. And you can turn just 1 lamp off in the fixture that is farther away from the window, because you need more light, more artificial light in the back of the room. With this situation, we might say that the artificial light level looks something like this. It's lower near the window and more higher in the back of the room. And the total light level might look something like that, where there are some slight variations, but overall it stays above our target set point, especially if we do the daylighting design right. So what constitutes a daylighting control? We have a sensor, obviously, that needs to sense the amount of light either inside the room or the amount of light outside, and we'll take a look at open loop versus closed loops the controls in a minute. So we have a sensor here. The sensor sends a signal to the controller, and then the controller presumably has been calibrated for that particular space and that particular design. And based on its internal logic and the signal that it is getting from the sensor, it controls relays, which then communicate to the dimming ballast about how much the lights should be turned down. So this is pretty much how the system works. Of course, there are different types of controls. There are closed loop daylighting controls. The basic philosophy here is that the sensor is placed inside the space, so it is able to look at the illuminance on the desk. And by doing that, it attempts to keep the illuminance by sensing how much light is falling on the desk. It can send a signal back to the controller and adjust that light so that the amount of light that it is seeing is constant. So, for example, if you set the target level to 50-foot candles, if it sees that there are 60-foot candles it is receiving within its field of view, then it will send a signal to the controller to turn down the artificial light and get the level back to 50-foot candles. So that's closed loop controls. There are also open loop controls, which don't look at the light level inside the space, but instead look at the light level outside in the outdoors. These can be useful if you're trying to control a large single zone, for example, where the light level within that zone doesn't change drastically. For example, with skylights, this may be a valid solution because the light level under the skylight is more uniform compared to a window. So what happens here, though, is that if you were to somehow change the interior light level without changing the exterior light level, there is no way for this system to know that. And so, for example, if you were to draw the blinds here, the system cannot respond to this change in light level. And what you'd end up with is your sensor is telling you that you have a lot of light outside, so it turn off the light, but on the inside you don't have as much light. So this can be a problematic situation. But of course, it works very well with skylights most of the time because you usually don't have blinds on skylights. Okay, I apologize for the colors in these charts. I was playing with this yesterday and trying to make it such that easily readable. I hope it is easily readable. I'm going to try to explain it. So light can be dimmed in steps. We saw in the previous chart, light being turned off, well, individual lamps being turned off. Essentially, what we are doing is we are turning off the light in steps. What happens here is, imagine that the sun starts coming out early in the morning. This yellow piece of the graph shows the natural light. And so the sun starts coming in the morning. It has still not achieved enough level to be able to turn off half the lights. But at about 25 foot candles, there is enough light coming in through the window that you can turn off half the light. So your artificial lights are providing 50 foot candles, which is our target foot candle level. When the natural light hits 25 foot candles, you can turn off half the lights. And so your artificial light level goes down to about 25 foot candles. And then as you start getting more and more natural light during the day, your total light level on the workspace goes on increasing until you hit 50 foot candles from natural light, in which case you can turn off all the lights, all the artificial lights. But you can see this sawtooth pattern in the total light that is falling on the work surface. It is more than what the minimum that we need. This is not usually a problem. I mean, 70 foot candles on the work surface is not a problem at all. But there are some opportunities for lost savings here. So we can probably get more savings if we were to do continuous dimming. What happens in that case is that once the natural light is above a certain threshold, say maybe 5 or 10 foot candles, you can continuously turn down the the artificial lights in response to the natural light and maintain a much more constant target level. This also helps with occupants because what happens in the step system is that the lights can go on and off and there can be drastic changes in the light level, which can be disturbing and uncomfortable sometimes, and some people may complain about it. Whereas in this system, the change in the light level is much more gradual, and so this may be preferred by occupants. You also get more energy savings because those sawtooth peaks that we were seeing in the previous graph, though they are not there in this graph anymore because we are maintaining a much more constant level here because of the continuous dimming. But of course, the trade-off is that continuous dimming is more costly. We have to use separate ballasts to be able to do continuous dimming. And the whole system is more costly in general. But the cost of daylighting controls at the same time is coming down significantly. So, your mileage may vary. You may be able to find controls that continuous dimming controls that are comparable in cost to step controls. Here are some factors that affect daylight control savings. Daylighting controls usually works best in spaces that have regular occupancy during the daytime. So spaces such as offices, schools, warehouses, even though they don't have occupants, regularly occupied spaces probably, they still have lights that need to be on, and so they make for good candidates for daylighting. Daylighting does not work very well in residential spaces, obviously because there is no one there during the day, and and if there is no one there during the day, you might as well turn the lights off, so you don't need daylighting controls to do that. It doesn't work well so much in spaces that need to be darkened. For example, in auditoriums, you can work it into a daylighting design, but it's difficult to do, as we saw with that classroom. There are some other spaces in which daylighting doesn't work very well. Retail spaces, for example, is an example. The savings also depend on the window size. as we see, codes and standards usually don't tell you how much windows to put on your facade, and so the amount of daylighting that daylight savings that you can generate will depend upon the size of the windows and how much daylight area you have. The window visible light transmittance is also an important factor. In the southern climates, the current commercial standards require very low SHGC windows. An SHGC of 0.25 is required in climate zone 1, for example. So the visible light transmittance of most windows is tied to the SHGC. You can, of course, get high performance windows where the SHGC is low and the visible light transmittance is high. That's an ideal scenario because then you can get the low SHGC benefits and you can get reduced cooling through that. But at the same time, you can get a large amount of light through a small amount of window area. And that way you can maximize your daylight savings. The control type, as we saw, impacts how much savings you can generate. Continuous dimming generates higher savings, but at the same time, the off step, being able to turn the lights all the way off, that is also a very important. Design or a step that can generate large amount of savings. If you're not able to turn the lights all the way off, there might be a situation where you have enough daylight but your lights are still on, and that can result in lost savings. The space type or the illumination set point is also important. For example, if you were to be doing a task which requires a lot of daylight, then you may not be able to get all that daylight in there without causing glare and so on. And so if you are targeting a very high, if your task needs a very high set point, you may not be able to get there all the way with daylighting. And so you may not see as much savings there as you would, say, for example, in an office space, where you can get all the target illuminance through daylighting. Lastly, daylighting controls require calibration, commissioning, and testing. This is very important to realizing the savings in the field. We can do the best daylighting design and specify the best controls, but if they are not calibrated, commissioned, and tested in the field after installation, then they're not going to work, or they may create uncomfortable situations and then they may get disabled. So this part is very important, and the codes and standards are paying attention to this part. So there are requirements in codes and standards to calibrate, commission, and test daylight controls. Appropriate sensor location is also very important. Sometimes reflections or placement near the windows and so on can cause problems. Also, direct, indirect pendant fixtures can it's tricky to locate daylighting sensors with such fixtures. So care must be exercised when locating the sensor. More and more occupancy sensors are required in codes now. Most spaces are now required to be controlled by occupancy sensors, and so configuring the occupancy sensors to work with daylighting controls is another important aspect that needs attention when doing the daylighting design. And finally, training owners, maintenance staff, and occupants is vital for daylighting controls to function correctly. As we saw in the previous slide, humans will find a way to make themselves comfortable, and so if you haven't thought of that in your daylighting design, you may not realize all the savings. All right, so that was an overview of daylighting controls. Now we are going to look at some of the requirements in the codes and standards. Codes and standards are interested in daylighting, obviously, because it saves energy. But at the same time, it is difficult to write language in codes or codified language that can capture the full savings potential of daylight of controls in a systematic manner. Buildings and spaces come in all shapes and sizes, and it's difficult to write like a one-size-fits-all solution. But at the same time, attempts have been made to incorporate daylighting requirements into the codes, starting with the 90.1 2010 edition. Previous to 90.1 2010, there were no requirements to put daylighting controls into buildings, at least not from code. So this table shows when requirements were introduced, what types of requirements were introduced, and these plus symbol, I'm using that to indicate the stringency of the requirement relative to other standards. So looking at side lighting controls, they were first introduced in 90.1 2010. Only the primary side lighted area was required to be controlled. This changed in 90.1 2013, and so that's why I'm indicating that with 3 plus symbols. In the 2012 ICC, also for the first time in the ICC, in the 2012 edition, side lighting controls were introduced for the first time, and these were made more stringent in the 2015 ICC. Top lighting controls follow a similar story. There are also requirements for putting in a minimum top lighted area in certain spaces. What that means is that not only do you have to have daylighting controls controlling your light, but if you have certain types of spaces, for example, high bay spaces in warehouses, you need to put daylight. You need to put in skylights, which is a component of the envelope, so that you have a daylight area in those spaces. And then you have to put controls to control the lights in those spaces. So there are 2 requirements in that case, not just controls, but also a requirement in the envelope section. These daylighting control credits, they are only related to the 90.1 standards. What these credits what these credits do is they provide a higher LPD if you go beyond the code requirements for daylighting controls. So for example, if you were to, in 90.1 2010, if you were to put controls in the secondary side lighted area, which we'll describe in a minute here, then you get a credit and you're able to trade that off with a higher LPD. So those credits exist in 90.1. There are no such credits in the ICC. And finally, there are requirements for some testing, which we just talked about. And we'll look at these in some more detail in subsequent slides. So we start with the daylight zone definitions. When you're all the codes, all the 90.1, all the 4 codes, 90.1, 2010, 2013, and the 2012 and 2015 ICC, start with a description of the daylighted area. Once you have a description of the daylighted area, you know that there are a certain number of lights in that area, and then you can have controls for those lights in that area. But it all starts with the description of the daylighted area. So this figure shows the daylight area under skylights. You can see that this is a description from 90.1 2010. For a skylight, the area extends to 0.7 times the ceiling height. If there are obstructions, then the daylight area may be reduced. And it depends on how tall the obstructions are. So for example, if you have ceiling height partitions, obviously that's a different space. But if you have cubicles, then it has certain requirements for how high the partitions can be and how they bound the daylight area. For skylights, if there are no obstructions, the daylight area extends to 0.7 times the ceiling height. So what we see here is what this equation does basically is if you have very tall ceiling heights, your daylight, a single skylight can cover a large daylight area. Similar areas are described, or similar definitions are put in for side lighted areas. Again, this is from 90.1 2010, and you can see that for a window, the depth of the primary side lighted area depends on the head height of the window. So the primary side lighted area, as described in 90.1/2010, extends to 1 times the head height. So it is equal to the head height of the window. So the taller the head height of the window, the deeper the primary side lighted area extends into the space. And again, it may be bounded by obstructions in the space. The definitions for the 2012 ICC are similar. So here we looked at the 2010 definitions. Now we are looking at the 2012 daylight zone definition. They are similar, but they're slightly different. For example, the floor to ceiling height, the daylight description, which is based on the floor to ceiling height 90.1/2010, it is just made equal to the floor to ceiling height in 2012, whereas in 2010 it was 0.7 times the floor to ceiling height. So it's similar but slightly different. And the same applies to the primary side lighted area, where it was 1 times the head height in 90.1/2010, but here it is fixed to 15 feet. So if your space, if you have a private office that is only 14 feet deep, then it would extend all the way to 14 feet. But if you have an open office that is 30 feet deep, then your daylight zone would extend only up to 15 feet from the perimeter. This is different from 90.1/2010 because generally window head heights are about 8 feet typically in office buildings. So 15 feet would mean that you're almost twice the head height in ICC 2012 compared to 90.1/2010. So this is something to be aware of. The descriptions in 90.1/2013 for daylight area did not change. There were some additional things that were added for clarification. For example, the overlapping area between primary side lighted areas and top lighted areas was clarified that you can't double count this area. And also a secondary daylighted area was described in 90.1/2013. So the primary side lighted area is 1 times the head height. The secondary side lighted area is 2 times the head height. All right, so that was about the daylight zone definitions. Now we are actually moving into the control requirements. So once you have described the area, you can establish certain requirements based on the area that falls under the daylight zone. So 90.1 follows this methodology. It has a threshold of 250 square feet for side lighting. So if you have more than 250 square feet in a daylight zone, you're required to put side lighting controls in. The primary side lighted zone depth, as we saw, was 1 times the head height, and the secondary side light zone depth is 2 times the head height, but you're not required to control that in 90.1/2010. You're only required to put in stepped controls because these are cheaper, and some steps are specified. So you need at least 2 steps, and 1 step must be below 35% of full power, and another step can be between 50% and 70% of full power. Similar I'm going to jump to 90.1/2013 here because the requirements are similar, but there is one major difference between 2010 and 2013. The type of threshold that was present in 2010 was changed in 2013. So in 2010, we were in an area threshold. In 2013, we are in a controlled power threshold. What that means is that if you have more than 150 watts in your daylight zone, then you're required to put in controls. So this requirement was not present, or it was differently specified in 2010. In 2010, we had, if the daylight zone itself was 250 square feet, you were required to put in controls. So that's the major difference between 2013 and 2010. Again, the primary and secondary side light zone definitions did not change between 2013 and 2010, but the major difference was that now the secondary side lighted zone was also required to be controlled in 2010, and you're required to have an off step in your controls. So in 90.1 2010, you could leave 34% of the lights on or 35% of the lights on, whereas in 2013, you could not do that. You would have to turn the lights all the way off. So that was an additional step that was added that saved a lot of, that generated a significant amount of savings. But designers should be warned in that turning the lights all the way off can throw some people off. They may think that the lights are not working correctly, or it can even create distractions. So while this requirement is in place, it comes with a warning that train owners and maintenance staff and occupants should be trained or should be told that this is how daylighting controls operate and this is normal operation. Yeah. Okay, so now looking at the 2012 and the 2015 ICC, as we saw the daylight zone definitions, there is just one zone definition. There is no primary and secondary. It's just 15 feet. And continuous or stepped controls are allowed, but they are not required. So you're allowed to do continuous dimming, or you're allowed to do step dimming, and there are some specifications for how much full power or what fraction of full power you must be at when doing continuous and step dimming. But these requirements were not or these are not requirements, rather they are just specifications. You are not required to put in daylighting controls in 2012, whereas in 2015 you are required to put in step controls and even continuous controls in offices and classrooms. And again, the other difference was in 2012 there was no threshold. You're not required to do anything with controls. But in 2015 or 2015 ICC adopted the 150 watt threshold in 90.1. There are quite a few exceptions to side lighting controls. I mean, we need to create some exceptions for things like retail spaces, for example, as well as for when there is not enough daylight potential available. Even though you may have a daylight zone described by your window, there may be an external obstruction that is very close to your window, such as buildings, high rises that are next to other buildings, and in that case you may not have enough daylight potential, and so you may not be required to do side lighting. There is an effective aperture requirement as well, or an exception as well. If your effective aperture, which basically ties the size of your windows to the amount of floor area that is daylighted, is not above 0.1, you are exempted from the requirement. Basically, what that means is you need a certain size of window for a given daylight area, and if you are not meeting that specification, then you are exempted from the requirement. There is no bottom threshold for minimum lighting power. We'll see in a minute for top lighting controls that there is a threshold for minimum lighting power. If you are in a warehouse and you have extremely high efficiency lights and you fall below a certain LPD, you're not required to do daylighting controls. There's no such threshold for side lighting. No exemptions for climate zones either. There are some other exemptions. For example, retail spaces are exempted, and there is a general exemption, I believe, for residential or dwelling units in the lighting section. Similar exemptions are there in 90.1 2013. There is also another exemption for when you have less than 20 square feet of glazing. So this sort of puts a bottom threshold on the size of the window. If you have less than 20 square feet of glazing, you don't need to worry about daylighting controls. And similar requirements exist in the 2015 ICC. There are no such exemptions in the 2012 ICC because, again, daylighting controls are not required. They only specify the type, for example, continuous and step, but you're not required to put in daylight controls in 2012 ICC. Now moving on to top lighting controls. Again, we start with an area threshold in 90.1 2010, and then we move to a controlled power threshold in 90.1 2013 and the 2015 ICC. The requirements are similar, but there are some specific features for skylights. For example, if the sunlight access is blocked for 1500 hours between 8 a.m. and 6 p.m., then you don't need to do daylighting. This may be again because there are exterior structures that are blocking access to the roof or sunlight access to the roof. There is a minimum lighting power threshold here in 90.1 2010 and 2012 ICC. If your lighting power density in the space is below 0.5 watts per square foot, you don't need to put in top lighting controls. Similarly, there are some exemptions for climate zones. In very cold climate zones, for example, in climate zone 8 in 90.1 2010 and in climate zone 6 through 8 in the 2012 ICC, you're not required to put in top lighting controls because basically skylights tend to lose a lot of heat in those climate zones, and so daylighting controls don't become cost effective in that case. And as I had mentioned earlier, the sole purpose of skylights is to save energy, and if you're not able to trade off the lighting energy savings with the heat loss, then it doesn't make sense to require controls. So that's why this exemption exists. Similar exemptions exist for 90.1 2013 and the 2015 ICC, but instead of having the minimum lighting power, we just have the watts, the controlled power threshold. So if you have less than 200 watts that are controlled, then you're exempted. This part of requirements was what I was talking about earlier, and it's usually in the envelope section. In fact, it is in the envelope section for all these 4 standards, and it relates to a minimum required top lighted daylight area from skylights. This applies to spaces which tend to be large. For example, the threshold in 90.1 2010 was 5,000 square feet. The 2012 ICC 10,000 square feet. And in the 2013 90.1 and 2015 ICC, it was reduced to 2,500 square feet. So these are kind of large spaces, and you can see that gymnasium, convention centers, warehouses, concourses, very large open offices probably, or large lobbies and atria. These are the types of spaces that are applicable here. One defining feature of these spaces has to be that the ceiling height has to be at least 15 feet. It then makes sense to put skylights in and then to put controls in. And it makes sense because controls are able to save lights and they are cost effective. So not only do you have to have a large space, but you also need a high base ceiling basically, or a high base space for this requirement to take effect. So there are 2 parts to the requirement. You can choose either 1 or 2. You must daylight at least half the floor area of the space, or the skylight. No, I'm sorry, this is not an either or. This is, both of these are required. You must daylight at least half the floor area of the space, and the scaled skylight area to daylight area ratio should be greater than 3%, or the skylight effective aperture should be greater than 1%. Basically, these say that for a given amount of daylight area, you need a certain amount of skylights to be able to daylight that area properly or sufficiently. That's what this requirement does. Again, you're not required to put in skylights in the cold climate zones. And when there are other conditions such as existing structures that block sunlight access, you don't need to do that. Again, you're exempted if your interior lighting power density is below a certain threshold. And again, you're exempted if there is other kinds of side lighting. If that part of the daylighted area is already falling under side lighting, you don't need to put additional skylights to daylight that area. Or if you have rooftop monitors and so on, then you again don't need to put in skylights. All right, so those were the requirements related to controls, side lighting controls, top lighting controls, and then minimum daylight area requirements for skylight. Now we are going to look at alterations. 90.1 10%, 90.1 2010 says that if you have greater than 10% of the connected lighting load in a space that has been altered, then you need to follow the requirements of Chapter 9. And provided, and also if your LPD increases when you do the alteration, only then do you need to follow the requirements. So daylighting controls are generally not applicable because only, I'm sorry, I should back up a little bit. This requirement only applies to LPDs. So only the lighting power densities must be complied with. Daylighting controls are not applicable to alterations in 90.1 2010. In the ICC, 2012 ICC, daylighting controls are not, therefore they are not applicable. In 90.1 2013, again, the alterations, you only have to worry about the lighting power density, and so again, daylighting controls are not applicable. When we come to the 2015 ICC, this is a different scenario. If your alterations go into the lighting chapter, then daylighting controls are applicable, and in fact, you would have to put in daylighting controls in your project. Finally, functional testing. It's required in 90.1 2010. The requirements are similar or the same in the 2012 ICC. In 90.1 2013, the requirements were slightly enhanced. I'm not going to go in the details of the enhancements here. And in the 2015 ICC, the requirements are the same as in 90.1 2010. So what are the requirements? The requirements are that the controls must be tested after installation to ensure correct operation. It should be confirmed that the daylighting controls actually reduce electric lighting in response to daylight. Placement and sensitivity should be checked. The documentation of testing is required. In 2013, you're also required to put on your plans where the daylight areas are so that the code official can easily identify the daylight areas. And then there should also be third-party functional testing, and the third party must produce a report that certifies that all the control requirements were met. So these are some of the requirements under functional testing for daylighting control. A brief summary of control credits for 90.1. I mentioned these earlier. For 2010, there are some credits that basically say that if you have certain controls, instead of step dimming, if you have continuous dimming, you get to increase your lighting power allowance by a certain amount. And then if you control the secondary daylight zone, then you get to put more lights in, basically. That second control credit was removed in 2013 because secondary daylighted areas were required to be controlled in the mandatory provisions, so you would not be able to get for it later. So that requirement was removed in 90.1 2013. So these are just some credits to be aware of. It can using these credits you can get some more lighting power if needed. That's all I have. I'm going to summarize quickly about all the things I talked about. I've been talking for an hour, so it's good to do a summary. We started with a brief overview of daylighting basics. We looked at illuminances, we looked at what side lighting is, top lighting is. Then we went on to some of the factors that are important for daylighting design, such as sunlight availability, interior surfaces, the human factor, and so on. From there, we moved on to daylighting controls, how they work, what are open loop controls, closed loop controls, and how daylighting savings are achieved, what the differences are between continuous and step dimming controls. And the last section that we talked about was the requirements in the different codes and standards. So that's what we covered today. I hope you were able to get some information out of the webinar. And I hope that you learned something new. If you have questions, you can send them to Pam, or you can type those in the chat box. And Pam, do you want to go over these last few slides?
Sure, thank you, Roel. That was a great presentation. Before we get into the question and answers, a slide on resources that are out on energycodes.gov. Couple of things. We do have compliance software for commercial energy code compliance. ComCheck Web, there's a screenshot of it there. We also have technical support, so we do have a help desk if you have energy code related questions or questions related to the software. ComCheck or ResCheck for residential energy code compliance. There are code notes that are available on specific code requirements that we have out on under resources on the website. Specific publications, energy cost analysis, and so forth that you might be interested in, some resource guides, and our training materials. We have the full set that we actually do for all of the main IECC and 90.1. If you're a trainer, that's great material to go grab. You don't have to pay anything. This is all free material. Take it, use it, customize it to your liking. But those materials are available for all the main baseline codes for ASHRAE and IECC. And if you're not a trainer, it's good information to go out there and take a look and see what's actually in all the codes, because it does have every code section in there and does have some speaker notes as well. That's all available out there on energycodes.gov. There's more information, so if you haven't played around with the website, it's a good time to go do it. And I also want to mention yet again, we are looking for more training topics. There was a couple questions that came in, asked about if there's any other daylighting software or daylighting training that's available. We don't have any specific daylighting training that we have geared up to do in the near future, but if you have some suggestions on other topics, even related to daylighting or other type of lighting controls or anything to do with energy codes in general, to do with commercial or residential buildings. We want your topic ideas. You can submit them through the help desk. You can submit them through the link that you were provided to the webinar today. And so there are some different avenues that you can go to and submit as your topic ideas. We are interested. So again, Roel, you did an awesome job. There are so many questions. We had a really large audience today. And I'm going to go ahead and start just addressing questions to you, Roel, and then you can answer them as we go along, and as time permits, we will try to get through all the questions that have been submitted, and ones that we don't, if your question doesn't get answered, again, you could submit them through our help desk, and feel free to do so. So let's start off with the first question. So Roel, how do the savings in natural light compare with the increased cost of air conditioning?
That's a good
I would just start off with a tough question.
That's a good question. So actually, when you have daylighting savings, they come from turning the lights off in the space, and so what you would see is your cooling load would actually decrease because the lights are putting out some heat together with the light, and so when you turn the lights off, you have less heat. And so your cooling load goes down, but you do see an increase in the heating load. As we saw in some of the requirements in the codes, skylights are not required in climate zones 6 through 8, which is basically the really cold climate zones. Climate zone 8 is Alaska. So in those climates, the trade-off simply doesn't work. You save some energy from the lights, but you're losing so much heat from the skylights, and also, you're losing so much heat from the skylights that that trade-off doesn't work anymore. But generally, for side lighting and for skylights, in many parts of the continental US, it should work. It is a positive trade-off.
Great.
I hope that answers the question.
How does one deal with build reflectance at very high lux levels? So build reflectance at very high lux levels.
See, could you repeat that? Sorry.
So it's how does one deal with build VEI-LED reflectances at very high lux levels?
Yeah, I mean there is you can't really deal with it. You have to do something about it, I guess. If you're getting that in the space, then I mean, I'm trying to imagine how in an office, if you're getting that, you're probably getting direct sunlight reflecting off some surface, or maybe it's an adjoining building which has a really reflective glass, and you may be getting a reflection from that. I mean, that can be really annoying, and I guess you need blinds or some mechanism to control that. And if you don't have that, that can become really problematic.
Okay. Next question. LED won't operate with ballast. Is the driver in LED lighting control the artificial light?
Yes, that's right. So there is a whole PNNL. We have a solid state research program at PNNL, and we are engaged in understanding how LEDs react to dimming. So not all LED drivers are capable of dimming, and even some of those that are capable don't do it very well. So you can get flicker, and you may get premature burnout, and so on when the lights are dimmed. So you need to get drivers that are compatible with dimming. But yeah, but they are available, and they should be commonly available. And it is, and LEDs are actually great for dimming because I mean, you can control them really very precisely and quite easily, and they are more amenable to dimming than say fluorescents.
Okay, so while we're still talking about LEDs, we've not specified fluorescence in years, and it was a comment that came in. And at this point, is there an update coming for LED fixtures? Some of this is no longer pertains, and I think this was in your beginning slides that you had when you had the table up.
Uh-huh.
So the question is there going to be an update for LED fixtures for specifications?
Yes, I mean, I'm understand the question. So in general, LEDs are moving at a very rapid pace right now. There are rapid improvements in the efficiency, and the cost is coming down quickly too. So in the next round of 90.1, which is 90.1 2016, and probably the 2018 ICC, you will see new lower LPDs that are based off of LED products. Especially in 90.1, I know that the committee has looked at what is available today and what is going to be likely to be available in the future, and there are some conservative updates to the lighting power densities. So the lighting power densities are moving downwards to follow the penetration of LEDs in the market.
Okay, next question. When using dimming ballast in the fixture, what is the range of the dimming ballast to be used?
I don't know if I can answer that question. I don't know. I would probably need more information to answer that.
Okay.
To be fully honest, to provide some background, I have not been a practitioner for like several years. I've worked in codes and standards, so I wouldn't be able to answer that question. But I can, if given more information, I can probably take a shot at it.
Okay, sounds good. What is driving the reduction in cost for daylighting systems?
That's a good question. I mean, in general, the cost of sensors and controls is going down. Sensors are becoming much cheaper, and it is also with LED lights. It's also easier to control the LED lights, as I was mentioning earlier. Yeah, I mean, basically, just the cost of the sensor and the controls are going down. the cost of the wiring and the commissioning and installation, that may still exist, but there are some ways around that too. I mean, nowadays you get wireless sensors which are more expensive to begin with, but they are much easier to commission. But of course, the trade-off then is that wireless means there are more things that can fail, and there are more things that you may have to maintain. So, so it's a trade-off. But traditional sensors and controls or controllers are coming down in cost. That's just driven by technology, I'm guessing.
Okay. In 2012, is there something that distinguishes the side lighting provisions from the top lighting provisions? Is it just daylighting control? Can you confirm? So is there I would have to say I can't even say it. Whereas distinguishing between the side lighting provisions versus the top lighting provisions in the 2012 IECC versus 90.1. Can you go into more detail about that? You might want to go to that slide where you have the top lighting and side lighting.
Yeah. I mean, there are some differences. The main thing I would say is that the 2012 ICC does not have requirements for daylighting controls. I mean, it prescribes things such as if you want to do daylighting controls, you must have continuous controls, or you must have step dimming controls. I'm sorry, I'm just going to go back to my final slide. It does prescribe the types of controls, but I don't think that they are required. You're not required to install controls. There may be some requirements tied to the envelope section, where if you do, I'll have to look in detail. If you do certain higher window to wall ratio, you may be required to put in controls, or if you have skylights in a zone and so on, you may be required to put controls. But at least in the lighting chapter, the daylighting controls are not required. They are optional.
In the 2012 IECC for daylighting controls, or all the provisions you've talked about. So in the 2012, is commissioning and testing required?
Yes, it is.
Okay. So this has to do with side lighted zones and the one times the head height and the secondary head height, Rahul. So
right.
90.1 over 2013. The secondary side lighted zones are only 1 by the head height in depth, but extend that depth beyond the primary side light zone. Isn't the 2 times the head height a misnomer to the depth of the space?
Right. That's true. So let's see. Why do I have that graph here? Yeah, that's right. This one. So yeah, it is. You can say that it is a misnomer. Yeah, the secondary side lighted area does not start until the end of the primary side lighted area. So it is 1 times the head height, but it starts at the end of the primary side lighted area. So yeah, I guess in my slides where I say twice the head height, I could change this to say it is 1 times the head height beginning at the end of the primary side lighted area. So yes, that is true.
Okay. Keep it on this slide. There was one about the wattage that I'm going to ask next. Okay. Yes, right here. So the next one of these questions was controlled power 150 watts. For a lighting area, what is the wattage referring to?
It refers to the lights that are placed in that area. So for example, if you were to look at a drawing of the lighting system, and you have certain luminaires in your let's take the example of a perimeter office, of a private office. If you may have say 6 or 4 2x4 fixtures in there. and you will have a certain amount of lighting power in that private office. And if that private office constitutes a primary side lighted area, then you have a certain amount of power in that primary side lighted area. And if that power exceeds 150 watts, basically you're required to put controls in. That's how it works. Yeah, so it might happen that your daylight, you know, in a large or in an open office, it might happen that your daylight area extends up to extends a certain amount, and there is just one fixture, like half of the fixture, that falls in there, which makes you go over the threshold. There may be some situations like that, but they should be rare, and they should be explainable with the code official.
Okay, so I'm going to try to combine a couple questions here, and maybe you can touch on this or summarize this, Roel. So there have been questions that have come in, a variety, on alterations. So if we have an existing building and we're remodeling it, and this I think is going to be code dependent, does daylighting controls come into play? Let's say if you're doing a lighting retrofit that's 100% of an actual space. Or can you talk more on the requirements for alterations on an existing building? And you have the slide up, so I think this might address some of the questions that have come in. And what path is this? Is it very prescriptive? Meaning if you are doing alterations and you're looking at daylighting controls, is this very prescriptive, or can you look at other methods of compliance when it has to come to these requirements for daylighting?
That's okay. I'll answer the first part first. So I just quickly, I think I was not clear when I explained this slide probably. So for these, so for 90.1 2010, 2012 ICC and 90.1 2013, daylighting controls just don't come into the picture, because the only things that are affected by alterations are the lighting power density or the interior lighting power density. So if you're doing alterations, all you have to worry about is the interior lighting power density. Daylighting controls are not in the picture at all. In the 2015 ICC, they are in the picture. So if you are altering more than 10% of luminaires in a space and your LPD is increased, then daylighting controls are in the picture, and you may have to put those in. But if you are not altering, if you are ordering less than 10% of the luminaires, or if you are not increasing the LPD, again, you're okay. So that's the requirement. The second part of the question was whether the performance path or some other paths could be explored. And I would have to refer back to the code before answering that question. I don't want to say something that may be incorrect. So if they want to, if the person asking the question wants to contact us later, I can probably look into the code or the codes and provide that answer. I'm not sure how the paths work and where alterations fall in the different paths, because there is a prescriptive path, there is a performance path, there is maybe trade-off approaches. So I'll have to look at that before answering that question.
Okay. I answered a couple questions. That you have some slides where you had a table with VT, visible transmittance, and it was asked what VT was meant. And so I'm wondering if you could touch on VT, go to the slide that had visible transmittance and the variables around VT. And this will answer a couple of questions that have came in about visible transmittance.
Right. I think there's
on retail spaces right there. So
yeah.
If you could just touch on VT a little bit, that might help answer some of the questions related to VT.
Sure. Yeah. So VT is basically the visible light transmittance. That is the total light transmittance coming through the window, including the frame. So there are certain exceptions here. VT also ties into the effective aperture. So the effective aperture includes the effect of the size of the window as well as the transmittance of the window. Basically, that just means how clear your window is. A very clear window, you can get a lot of light in. Whereas if you have a dark window, you may not be getting as much light in. I mean, essentially that is what VT characterizes, visible transmittance characterizes. And so what the effective aperture says is that if your window is either too small or too dark to provide enough daylighting, then you are not required to provide controls. It's the same with and it's the same with skylights too. If the VT is below a certain threshold, then again you're not required to provide controls. But I would suggest looking at the requirements in detail because there are certain exceptions, there are certain other requirements too. So I would suggest looking at the requirements in detail when it comes to VT. There is a thing called the haze value as well that applies to skylights. I don't think I have it here. So what the haze value means is that the skylights need to be you don't want to let direct light in through the skylight. You want diffuse light to fall through the skylight, and so the skylights are fitted, or they're sort of hazy in terms of the texture or the or how they look. And basically, that diffuses the light coming in through the skylight. So there is a requirement in the standards for that too. And that's sort of related to VT.
Great. In the IEC, next question, are there any standards in the IECC for K temperature, Kelvin temperature, mixture of artificial versus natural light? Is there any reference standards?
Sorry, could you repeat that again?
Are there any standards or reference standards in the IECC for K temperature mix of artificial versus natural light or natural light?
I
don't believe there is.
I don't believe there is, no. So the ICC and even 90.1, they're primarily concerned with with energy savings. And I guess what this is getting at is the color of the light. I don't have the question in front of me, and we can't talk to the commenter, so I don't know what the question precisely means. But if it refers to color, then no, there is no guidance in or a requirement in the ICC for that. But I would look for the IES, the IES handbook, or one of the recommendations, or the I don't know what they call them, the standards, the IES standards for that information.
Okay, great. This is back on the visible light transmittance, I'm not sure that there's an answer for this, but I'm going to ask you anyway. Is there a visible light transmittance value that will reduce the potential for glare or eliminate glare?
That's a good question. So I mean, you can put dark windows in there. That will definitely reduce the amount of light coming in. And so if you have, like, if you are wearing sunglasses, for example, you can probably look straight into the sun as well. Probably not, but for some time maybe. So you can get tinted windows, dark windows, that will probably help with the glare. But I don't think that's good daylighting design. I think the way to do it would be to have clear windows so that the occupants have a view to the outside, and then you should have blinds on the inside so that the occupants have control, so that when there are situations where there is glare, they have the ability to control their environment and avoid the glare. Also, good, with some overhangs, you can generally avoid summer direct sunlight in most parts of the country. So there are some other ways to avoid glare, I would say. Definitely blinds are probably the best way.
Okay. I'm kind of going through some of these questions, as we've answered some of them because they've been multiple together. But there was a question, Raul, on slide 10, and it had to do with if you could further define the sky types A, B, and C.
Oh.
And the map that you've referenced, what was the reference that you shown on the map?
Yeah, I think this is from the IGCC. The IGCC, I don't know, I don't remember which year, but this is from one of the IGCC standards, which is a green standard or an advanced standard, advanced version of the IECC. So, but originally it comes from NOAA, and it's a chart showing the annual mean sunshine percentage. There is a legend here too, which I edited out. But basically, it talks about the amount of sunshine that is available in different parts of the country. I mean, in most parts, there is enough sunshine available. It differs, of course, but you have to be wary of Seattle and probably along the coast here and some of the more cloudy regions. That may warrant a different daylighting design where you probably have, for most parts of the year, you have diffuse light, and that will affect your daylighting design. The size of the windows, for example, and what strategies you use to control glare and direct light, those are the sort of things that will be affected.
Okay, so there's been some questions that have came in about states and who adopts daylighting controls and so forth, and I'll address that, and then I have one question left for you, Raul, and then we will wrap it up. If you could put it on that last slide again. And then again, if we didn't address your question, send it in through our help desk. The link is also provided on this slide here. So there were a couple of questions that came in and said, well, who has these daylighting controls and where are they enforced and what states have adopted them and so forth. There was a question that came in on an older code, the 2009 IECC. States adopt different versions of the codes throughout the entire U.S. Some are still on the 2009, some are on the 2015 IECC, and some directly enforce 90.1 2013 and vice versa. A good resource to go to see what state has adopted what code, you can go out to energycodes.gov and you can click on adoption, and there is a drop down of every state, and you can click on the state and see what the active effective energy code is in that state. And as Raul has talked about today, he was referencing the most recent two versions of the 2012 and 2015 IECC and ASHRAE 90.1 2010 and 2013. That doesn't mean that these are the only codes that are effective in certain states. And then some states are home rule and they adopt by local jurisdiction. So if you're a designer and you're not sure, first place, maybe go look at the state level, and secondly, you might want to work with your local jurisdiction to see what they're enforcing in their municipality. And last question to you, Royal, is where do you see the future of daylighting controls going? To sum it up.
That's a great question. I'm not the expert or anything. I've just been, I've been familiar with these things, but I'm definitely not an expert. But I mean, definitely LEDs are proliferating rapidly into the market, and the lighting power densities are going down too. I see at the same time there are phenomenal progress. There is phenomenal progress happening in technology, especially in the field of sensors and integration, of different technologies. So I think that luminaires, LED luminaires with integrated sensors that are able to, with the logic encoded in them, to automatically to sense the light and automatically reduce lighting, to automatically reduce the light level in response to that light. I mean, I think that is probably where we are headed eventually. These things do exist right now. You do get luminaires with integrated sensors and controls. They are expensive though, although I don't know, maybe the cost has come down, but definitely that's someplace that is likely where we are headed. And I'd also like to add a little bit to what Pam said. The 2009 IECC and the 90.1 2007 do not have any daylighting control requirements. So if your state is on, or if your jurisdiction is on those codes, there are no daylighting control requirements. And the second thing is there can be amendments. So even if your state adopted the 2015 ICC, they may have amended the daylighting control requirement. So there is always that. So you should refer to what your state has adopted for the code.
That's exactly right. I was just going to make that point. Some states do modify and have amendments to the codes, and some states have their own state-specific code. So you really need to pay attention to what's happening within the state. The best resource to go to is go take a look at those state pages out on the Building Energy Code DOE's website, and there is links out to even the state pages and resources if you want additional information on what's happening with their codes and their adoption of codes. And if you want to look at lighting in particular, there's committees that you can get more interest in if you want to. There's an ASHRAE lighting committee. There's lots of good resources out there that are available. And again, if you have questions and you need additional information, send it in through our help desk. Well, thank you, Raul, for taking the time. This was a great webinar that you presented today. There was a lot of questions that came in, a lot of really good questions. And we do appreciate you taking the time. Again, send us in your topics. We are looking for additional topics where we want to know what you're interested in when it's related to energy codes for training. We will be doing training every month, the same time, every second Thursday. So pay attention to out on the website for upcoming training webinar events as well. And everyone, thank you for participating today, and you can disconnect.